So we're starting some new content here. We'll go ahead and get started on page 380. We're talking about molar volume, or we could say volumes of a gas. And then what they're illustrating is, notice on figure 12, when you look at the very top, okay, it's just showing a chemical reaction between hydrogen and chlorine, then gives you 2 molecules of HCl. So you can see you have that law of conservation of mass, and we know that that's the case because if you have hydrogen, you just don't write it like this, okay? Why is this incorrect?
Because you need 2 hydrogens.
Okay? Because this is diatomic, and so is that one. So then what we see then, once you balance this, okay, so you have a molecule of this is what they're showing, and then, of course, you have a molecule of this, okay? So then, once that gets over to this side, we can illustrate that the equation is now balanced because you have one of those, and then this is mixed with that, okay? We have 1, 2, I don't know, red or orange circles on this side, 2 orange circles on that side, 2 blue here, 2 blue there. So that's just a maybe a shorthand way of looking at a picture to show how and why these gases interact, and that you have the same amount of gas on one side as you would have on the other. Okay, so when we're looking at molar volumes of a gas, what you're going to like to see is when gases are measured at STP, that is your friend. That makes things a heck of a lot easier. It doesn't mean that you can't solve for gases, because there's the ideal gas law that takes into consideration when these are not measured at that standard temperature and pressure. But anyway, page 380. Recall that 1 mole of a molecular substance contains a number of molecules equal to Avogadro's constant. Of course, we remember that from last August in September. 1 mole of oxygen contains 6.022 times 10 to the 23rd diatomic oxygen molecules and have a mass of 32 grams. 1 mole of helium, a monoatomic gas, contains the same number of helium atoms as the mass of helium, which is 0.002602 grams. We would just go by 4 grams. According to Avogadro's law, 1 mole of any gas will occupy the same volume as 1 mole of any other gas at the same temperature and pressure, despite mass differences. Okay? Which, one of the things that we wanted to illustrate, that meaning maybe a trick question, is that when you put Boyle's law and then you have Charles's law, what happens when you do this? Combined gas law. So then what you might want to ask yourself is, and that's why we stated this yesterday when it came to picking the pigeon, when you are at higher altitudes, is the pressure higher or lower?
Lower.
It's lower, so what are the gas molecules doing? They're spreading out. Okay? So then what about with temperature then? When the temperature is lower, what are the molecules doing? They're spreading out as well. So then in lower altitudes, when you would have maybe, I don't know what we just gave an example in the problem and said, if you're at this altitude or this altitude, when you're using the combined gas law, okay, if it's a higher temperature, okay, would the molecules expand or contract?
Contract. Wait,
At a higher temperature?
They're going to go closer together and squeeze.
When it's hotter?
Yeah. No, they're
They're going to expand. So you said that just the opposite. In Boyle's law, at a higher altitude, the pressure's less, so the gas molecules are further apart. Okay? So then what happens according to Charles's gas law when the temperature goes down? What does the volume do? That goes down. So you had to pick the pigeon that was going to maybe get the most oxygen per breath. But is that going to be because of Boyle's law? Is it going to be because of Charles's law? You really don't know. That's why you combine the two, and that's why we said this is kind of a trick question. So I like that because hopefully it makes you think that that's why you combine those gas laws, because is the amount of oxygen going up or is it going down? So that's why it is our job to make you think. I don't know whether you like that or not, but, and maybe you just never thought about that much. Maybe you just read the problem and said, okay, I'm just going to put V1, T1, P1 here, and V2, P2, and T2 here, and then whatever the numbers fall, that's what we're going to deal with. Okay. But
Well, they're used to it. Yeah, I definitely did.
according to Avogadro's law, 1 mole of any gas will occupy the same volume as 1 mole of any other gas at the same temperature. Oh, we said that already. The volume occupied by 1 mole of a gas at STP. And it's only when it's at STP. And this is a constant, is known as the standard molar volume of a gas. It has been found to be 22.4. Of course, you have some more digits on there. We just use the accepted value of 22.4. The standard molar volume. Knowing the volume of a gas, you can use 1 mole for every 22.4 liters. So what that means, that is your conversion factor. In other words, so for every mole, you have 22.4 liters. Why do we say that's a conversion factor? We've been using those. You have this one. That was a conversion factor. What was another one we did?
700.
Yeah. So we've been using these. Now we're just applying a different type. Now we're using moles and volume instead of 2 types of pressures. It's just a conversion factor that allows you to change a known substance, whether it's a number of moles or whether it's a mass of a gas, because we can change mass to moles, right?
Yeah.
So it's easy to take that mass, convert it to moles, and then once we get it into moles, now we can find a volume of that gas. So I remember one of you was asking about the combined gas law, and it would pertain to this too. Why would you want to know, or how do you use the combined gas law? What are some of the applications? Well, I think one was, like we had mentioned, balloons is a good application of that, especially, or blimps, you could say. But one that had intrigued me would be, unfortunately, if someone is in a car accident, but this is a life-saving ordeal besides the seat belt, the airbag. So there's a type of gas that's inside of that will expand, and because of that, there's certain stipulations that you'd want to use in I suppose, I wouldn't say a gas cylinder, but that it has to be stored somehow. And then I suppose when a computer system monitors that something has happened to the chassis of the vehicle, that airbag just then automatically deploys. And what gas that is, I don't picture it being oxygen or anything else. I'm guessing it's probably something that's a lot heavier than that. And what is it? That I really couldn't tell you. Okay, so we have this conversion factor of every mole will give you 22.4 liters only when it's at STP, okay?
So that can only happen at STP.
Only at STP. You can also use the molar volume of a gas to find the volume at STP of a known number of moles or known mass of a gas, like we just said. Because when you find the moles of any substance, it's not that hard to take that from a mole to find a mass. Then what you're going to find out when we get to the reaction stoichiometry, it might result in something like this, how oxygen gas was essentially discovered by Joseph Priestley, I think is who it was, 1700s maybe. So how could we get oxygen gas from that substance? In other words, what would this maybe resemble where you have something here and then something plus something else? Yeah, a decomposition reaction. So you have to have some way to break that apart. So you'd have to have a catalyst. Of course, that would be heat, and then you break that down into mercury and then plus your oxygen. So what gas reaction stoichiometry would say, since we have this conversion factor, if it's at STP, and if you're writing this down, fine, it's not going to mean anything to you, but it will come full circle at some point. You can make a conversion because of that, or you can do it with this, the ideal gas law. Because here, we're just talking about gases and gases only. In other words, just nitrogen only. Just oxygen here only. But with gas reaction stoichiometry, maybe you have 84 grams of this, and because it's gas stoichiometry, we might say, well, how many? It's not just this. We can do that. We've done that. A mass to a mass problem. But what you can do, because of these two different types of problem solvings, it's not just the mass that you could find, but maybe how many of that, how many liters, how many milliliters, or in this case, I think, don't we have cubic centimeters up here? Yes. Cubic centimeters is the same as a milliliter. So that's where this gets to be a little more difficult when we get to the gas reaction stoichiometry. Don't worry, I told the seniors, and they said, oh, we'd be willing to, well, besides our lone one in here. Of course, I think, you know, I don't know if they started pulling their hair. No, they didn't start pulling their hair out, but they remember these days. Okay.
I mean, I hope so. It was only a year ago.
So it was only a year ago. So there are some sample problems that you see at the top of page 381, but you can do that on your own, and then notice that that gas is measured at STP. Remember, we said makes things a lot easier when things are measured at STP. It doesn't mean that you can't do these problems. It just means that you would be turning the page, and at the top of page 383 is talking about the ideal gas law, which would also deal with gas stoichiometry. Yes?
So if it just gives you the moles, you don't need to do anything with like the grams because it's already done that like conversion. So you
Correct.
just would divide it by 22.4.
If you're just looking for a volume. And I think we have both types up here. So we'll answer that question here shortly. Okay, so we're going to be doing 4 problems. In other words, these 2 that you see on page 381. Then we'll go ahead and do an example like that. Anyway, practice problem number 1. It says, at STP, what is the volume of 7.08 moles of nitrogen gas? Okay, so there's only one place to start. You have 7.08 moles. Yes, and some of you are still going to do this. It hasn't changed from year to year. I still mention it from year to year. And students are still going to do this. And then they're going to ask questions. And then I'm going to say, if you're not going to help yourself, I really don't know how to help you. Yes? Oh, sure. Is it just the color, or is it where you're sitting?
No, it's the color. Yeah, I don't have my glasses on in the way like this.
Okay. Well, see, you're too kind. You could have said that that light is reflecting off my forehead and blinding you. See, you're just too kind. That's probably what's happening. You just don't want to say that.
You're just so bright with knowledge.
See, I like that too. But yeah, I don't think that's the case. Okay, so 7.08. Is that better? Okay, still, don't do this. Okay? Okay? Because what are we dealing with?
Nitrogen.
Right. And then don't just do that.
What?
No, you're asking a valid question.
And
Nitrogen gas, so like
Say that again.
and two,
Why is that?
because you need two nitrogen.
Yeah, because it's diatomic. Because what happens if you're looking for a mass of that? If you don't have that, chances are you're going to put 14.01 instead of 28.02. So we're looking for a volume of this. And what did we say earlier? What was our conversion factor?
22.4.
Okay.
2 point. Yeah.
So for every mole of a known gas, okay, for this mole of this known gas of nitrogen that's measured at STP, we know how many liters is that?
22.4.
22.4. It's just the conversion factor. Just like you'd use 9.8, just like you'd use 3.14, it's just a constant that has been calculated that the math actually works out. So upon doing this, the author says you should get 159. Okay? So these two numbers are next to each other. 7.08 times 22.4, then that gives you it might give you 158 point something, but then because of significant figures, that's probably why they round up to that.
So you do 159 liters and two?
Liters of N2, okay? And then notice everything's canceled out. You are left with just the L for liters because that's what we're looking for. And we're done. Okay, providing you say that you get 159 for that.
I sure hope so.
Okay, because one of the things that, again, I personally disagree with how little time the author spends on gas stoichiometry. That's why we want to do our own little, you can almost say, unit on that. Okay? So then practice problem number 2 would say, or does say, sample of hydrogen gas occupies 14.1 liters at STP. How many moles of the gas are present? So here you could say you are just moving backwards because you're starting with a volume first, which was 14.1 liters. Okay, and I know you're not dealing with a mass. Okay, I still would highly recommend, nope, it's not nitrogen. And I would recommend writing the right gas. Okay, then now that we've got our liters of H2, we want to know how many moles of this are present. So then how do we cancel this mole out now?
You put 22.4 on the bottom.
Right. So 22.4 sometimes goes on the top. Okay. Sometimes 22.4 goes on the bottom. It just depends upon what number you're starting with. Just like a molar mass, if you had X amount of grams, you want to know how many moles there are. Well, then your periodic table says, well, you need to have the grams, moles, hence molar mass. Or if you're starting with a certain number of moles of X, well then, okay, how many grams is that? Well then your moles goes down here, your grams goes up here, hence a different way of a molar mass. Sometimes the grams went on the bottom, sometimes the grams go on the top. Okay. Front row, are we on the bus here so far? Middle row, back row. Okay.
Yes.
So once we do this, this gives us our numbers of moles of hydrogen. So what we're going to see when we look at these two types of problems, there again, the author doesn't go that far in depth or maybe just doesn't spend any or even enough time on it. That's why we want to go over problems like that, because when you divide these two out, you get 0.629 or something like that.
0.6294642.
Okay. So then,
0.63.
You're off.
That's what I get.
oh, okay. You're just doing two to the nearest hundredth. And then that's fine. That's typically what we say is round to the nearest hundredth. 0.63, then that would be moles of hydrogen. So notice one of the things that we can do is if you had a volume of a gas, and if it's measured at STP, we can certainly find the mass of that gas from the volume. Usually it was just a mass to a mass problem. This is just throwing that extra, I don't want to say step, but it's just a different approach where instead of a mass to a mass, you're taking a volume and you could change it to a mass. Because we could certainly find how many grams of hydrogen are present in 14.1 liters of hydrogen at STP, because now that we've got that in moles, what would our final step to be to say how many grams is this? And this is maybe more familiar territory. How do we get rid of that mole?
Put moles on the bottom and then times it by.
And you laugh if you want, okay? People are either going to do this or they're going to do this. And then when they get their answer, they're going to say, why am I off by a factor of 2?
Because you gotta put it on the bottom of H2.
And that's, you should, even if you're not looking for the mass, because we're not looking for the mass here, okay? Even though you're not, you should always carry that, okay? You should always carry it. Then I always like to say, no matter how heavy it is, always carry it.
Yep.
Giggity goo.
We told a funny. Yeah.
We told it once.
Yeah, we told a funny. I did that yesterday with Next Hour, and I thought it was hilarious because it just occurred to me right at the moment was, I got to do this. I have to. But we don't need to do it today.
What?
Oh, well, you mean you say you can't say you're going to do something and then not do it?
Yeah.
Sure we can.
Gonna hold on to it, then you do it.
Okay, well, what I mean by that is, okay, they're doing dot diagrams. So I said, okay, so if we have lithium, and we know that you have to have 2 of those, okay? So you would, yes, I said, technically, I would say, we could say that that's right. But typically, you split your 2 positive ions apart. You would put 1 lithium here and 1 lithium over there. So I said, and you can use, of course, anything or any shape or whichever. So then this is a more appropriate way, I'd said. And so I said, this is a better way because that's no lie.
Oh.
See, that's no lie. We told another funny. No lie. Yeah. Okay. So, I know, it was a good one, wasn't it? And that occurred to me just like that when I was, I got to put an E here and say this is no lie. Okay. That was another one I did. I said, bro. I go, bruh, or bro. Isn't that what you young people, I didn't say that. I just said, bruh.
Isn't that what you young fellas?
Nah, that's right. Got to get with the program, I know. Okay, so these are maybe just a little more extensive. There's just one extra added step than what the examples are we saw in the book. Okay, so if there is 3.1, or you got to be able to read first. If there is 3.418 grams of nitrogen, how many liters is this at STP? And again, you will be solving problems like this when it's not at STP.
Yeah.
No.
You gotta convert it to STP.
Yeah, you can't. No, you wouldn't do that. There's just certain stipulations that you would have to know. because that is your ideal gas law. Now, this is a little bit down the road, but if it's the ideal gas law, you have that, you have that, you have that, you have that, and you have that. Okay?
Sigma.
So then what that means is when we define STP, what variables can you extrapolate from that? Yeah, because we got a temperature and a pressure. At STP, if it's standard, this one is 1 and that one's 273. So it's not like it's totally unknown. There's just a couple extra added steps in there when it's not at STP. That's why we said you're going to like it much better when these are measured at STP. So regardless, we've got 3.418 grams of nitrogen. Okay? So
And 2.
I'm going to say, what's wrong with this? Okay? So we need to get to, okay, so how many liters? Well, how can we convert a mass into a volume when we're not doing density? You have to go through that conversion factor. So how do we get rid of our grams in our next step?
The atomic mass of N2.
So 28.02 grams of nitrogen gives you one what? So now we're back into familiar territory again, because now we're in moles of a substance. So our grams are gone, and like we had done on those examples on page 381, we're in moles of nitrogen. How do we get rid of that?
Mole on the bottom and then 22.4.
Correct. So for every mole of nitrogen at STP, you're going to be given 22.4 liters of nitrogen gas, because again, it's measured at standard temperature and pressure. Okay? So again, this is what we call composition gas stoichiometry, because we're just dealing with one substance. Eventually, you're going to be dealing with reaction gas stoichiometry, where you have to convert one substance into another. And this doesn't have an answer key or whatever, because it's not out of the book. So we need to take 3.418 times 22.4, and that gives you 76.5632. We can just divide that 28.02. 2.73 liters of N2. Okay. So I suppose at some point down the road, maybe when these automakers are, what I want to say, inflating the, and maybe it's a chemical reaction, I could see that happening too, that will inflate those airbags. Because notice that one of the things that we had done a couple chapters ago would be maybe if you had something like, we could say, I don't know, some calcium plus some water. Okay. Well, then this would go through we could say a single replacement reaction, calcium oxide plus H2. So then one of the things, if we certainly needed a certain amount of hydrogen, one of these is going to be your limiting reactant. And maybe it's the calcium. Let's say this is your limiting reactant, and you need to produce, per se, 3.50 liters. Okay? And if this is your limiting reactant and you need to have 20 grams of this, but if this is your limiting reactant, what happens if you only start with 15 grams of this? What's going to happen to that number? It's going to be down. So that's, I would like to think, is a practical application on what somebody figured out a long time ago that's way smarter than myself, that, okay, this is going to be a practical application that we can put in high school textbooks to make them go crazy. Bruh. Yeah. Okay. All right. So that is when you have a mass and you're converting to a volume. Okay. Well, what happens if we have this within a tire? There is 1880. I should have put 1881.
Sure.
Because what does that have to do with SDSU? Do we know?
Foundation.
That was when, and Dakota State, I think, was founded in 1881 too. I think so. But I put 1880. I don't know. That's just what I wrote. So cubic centimeters is the same as a milliliter, but we have this oxygen. So how many grams is this at STP? Notice here we started with a mass, we converted to a volume. Now we're starting with a volume and we're going backwards and can convert that to a mass. So we have 1880. Now, when you see cubic centimeters, we can make this intuitive leap and say that is milliliters, so that makes this just a little more tricky. So you can do some math in your head, or you can show this extra added step, because we can't use this number.
Change to liters.
You have to change it to that. So you can show this. So we can do this instead. We could say we've got 1,000 milliliters, and that gives you a liter. Or before you even start, you can do what with this decimal then?
Move it to between the 1 and 8.
You can do that. You can say 1.88 liters, or you can put this step in here, whichever. Okay? So that gets you into liters. Okay? So how do we get rid of our liter in our next step?
22.4.
Because since this is measured at STP, for every 22.4 liters of oxygen gas, that's going to give us a mole of oxygen gas. There again, if you don't carry that, you're going to be off by a factor of 2. And then in this case, everything has canceled. We are in moles now, so let's get rid of this mole of O2 and then say we get 32 grams of oxygen gas. So now those have canceled. So we multiply by everything across the top, but rather than, you could say 22,400. If you want to leave it like this, you could say, or you could say 1.88 times 32 divided by 24, or you can take 1880 times 32 and then divide by 22,400. But then you might be asking yourself, now, wait a minute, what is it that we're actually starting with? We're not looking for a volume, we're starting with that, so we don't have to be worried about whether it's milliliters or liters. So you're going to get two different answers, and I'll show you what I mean. Okay, so 1880 times 32, and then divide by 22,400. Okay, so this is what you would get if we just left it, or if we have it in liters now, 2.69. 2.69 grams of oxygen. And sometimes it's going to say we want this to be in milliliters instead. But either way, that works. Okay. But again, when we say you can do this two different ways, it's whether you say 1.88 or you take 1880 and then divide by 22,400. Either way, you're compensating for that changing of milliliters to liters. All right, so that's all I have. We'll catch up to you next time.
I sure learned a lot today.